In this presentation, I want to discuss the model of tau-equivalence of classical test theory, and I want to show you how you can fit this model in the Mplus software and why it can be useful to look at this model. The tau-equivalence model of classical test theory can be described by a simple measurement equation where yi indicates a measured variable or observed variable for test I or measure I. Tau indicates a common true score variable or latent variable. Epsilon I indicates a measurement error variable for that test I. We can depict this model in terms of a path diagram. For example, when we have two measures that we think might be tau equivalent or for which we want to test whether they are tau equivalent, then we can depict them as y1 and y2. And the model implies that they both measure a common true score variable or factor in the sense of confirmatory factor analysis. So this implies a one-factor model, and it implies a special one-factor model, namely one in which the loadings are both fixed to 1. Because you can see that in the measurement equation up here, there's no factor loading parameter before the tau, and so this means that then implicitly there is a coefficient of 1.0. So when we specify this model, for example, in Mplus, we have to remember that the factor loadings have to be fixed to 1. So the tau equivalence model implies that both these tests or any tau equivalent tests measure the same common factor with the same loading. Furthermore, we also can depict the error variables in the path diagram, and so each test has its own measurement error variable. In this model, we estimate the variance of the true score variable or true score factor and its mean. And we also estimate the error variances. Each test can have its own error variance, which means the variables can differ in the amount of measurement error variance. Now, what is this model good for? Why is this useful? Why would you consider fitting this model to a set of tests that you have? For example, if you want to find out whether two tests measure the same construct, or in other words, whether two tests are unidimensional, then the tau equivalence model is one model of classical test theory that can be applied and that can be used to test whether the indicators or the tests fulfill this assumption of unidimensionality, whether they are tau equivalent. Now, there are other unidimensional models of classical test theory that will make either more strict assumptions or less strict assumptions, but this is one model that allows you to test for unidimensionality of the measures, and specifically for that assumption of tau equivalence, which means that the true score variable is the same for different tests. Furthermore, in addition, so to say, to being able to test that assumption of tau equivalence with this model, we can also use this model to determine the reliabilities of the measured variables y1 and y2, or any additional variables that we might have. The reliability coefficient can be directly computed based on the parameters that are estimated in this model. Remember that we're estimating the true score variance as one parameter in this model, and we're also estimating each error variance. And so based on the variance components, we can then calculate the model implied observed variances. So for example, for y1, the observed variance is given as the sum of true score variance plus error variance under the model. And so that sum of those two variance components then is in the denominator for the reliability coefficient. So we're dividing by the total model implied observed variance. In the numerator, we have the true score variance. And so the reliability coefficient gives us the proportion of variance that we observe in a measure that is true score variance. Or in other words, we could say the reliability gives us the proportion of variance that reflects true individual differences in a measure rather than measurement error. And that's very useful to know because we want to know about measurement precision. We want to know oftentimes how reliable are our measures. And so then by fitting the tau-equivalence model, we can find out, provided that this model fits our data well, then we can derive this reliability coefficient for each of the tests from the model parameters. Now I want to show you how you can get all these things in the Mplus software for a simple example with two measures. Here we have an example where I want to see whether two tests Y3 and Y4 are tau equivalent. And I can fit this model even with just two measures. Now it has certain disadvantages when you have just two, and you get a stronger test if you have more than two measures that you consider, but the model is identified and over-identified even for just two measures, so we can apply the model here to this set of variables. How do we do that? We specify a factor model in Mplus, confirmatory factor model, and we call our factor tau or whatever you like. You could also just call it F for factor or T for true score or something like that. And then you say tau is measured by Y3 and Y4, each with a fixed loading of 1, because the model of tau equivalence implies fixed loadings, implies that the measures have the same loading because they're assumed to measure exactly the same true score without any loading differences or intercept differences or something like that. There cannot be any mean differences between the variables. There cannot be any differences in the units of measurement between the variables as implied by this model of tau equivalence. And so therefore we also have to fix all of the additive constants to 0. Those are the intercepts that Mplus would estimate by default for all variables. And the tau equivalence model has no additive constant in the measurement equation. Therefore these additive constants or intercepts have to be fixed to 0. Now let's take a look at what the free parameters are in the model, and I made those explicit here, although you wouldn't necessarily have to do that for all parameters in Mplus. One parameter that you do have to let Mplus know that you want to estimate it is the true score mean, because by default Mplus does not give factor means and assumes that the factors have means of 0. So I requested the estimation of the tau mean by putting that label in brackets and then putting a star there. So then Mplus will estimate the latent mean. It'll also estimate the latent true score variance, which is the more relevant parameter typically, because that's what we use to estimate reliability. And that parameter would be estimated by default in Mplus, so you don't have to necessarily specify that explicitly. Also, Mplus would by default estimate the error variances as residual variances for the observed variables, so you also don't have to make that explicit, but I did put that in here so you can clearly see what the 4 parameters are in this model. Now, this model has 2 variables, and so for 2 variables we have 2 means that are observed, 2 variances that are observed, and the covariance between Y3 and Y4. So we have 5 pieces of information. The model only estimates 4 free parameters, so the model has 1 degree of freedom. Even with just 2 variables, it's over-identified, it can be tested. Now, what is being tested here? The only assumption that's being tested here with this 1 degree of freedom is that the variables have equal means, because the tau equivalence assumption implies that there's a common mean, that those measures do not differ in their means in the population. And so that's implied by setting the intercepts to 0 and estimating only 1 mean for tau, and so therefore the means are implicitly constrained to be equal by the model, and that's what our model test tests. Now, if you have more than 2 variables, then the test would be more stringent, so to say, because then not only would the assumption of equal means of all measures be tested, but also the assumption that all measures have equal covariances in the population. We cannot test that obviously with just 2 measures, because with 2 measures we have only 1 observed covariance. But if you had, for example, 3 measures, then there would be 3 observed covariances, and the model would imply that in the population these covariances are equal, and so that would provide additional degrees of freedom, and then the test would simultaneously assess equality of means of all variables and also equality of the covariances of those variables. Now let's take a look at the output for the simpler example. First of all, let's check the model fit. You can see we have a decent sample size here, 466 cases, so there should be sufficient power to reject the assumption of equal means if it's violated. And let's take a look at the model fit. You can see that the model has 1 degree of freedom, as I promised, and that's from the test of equal means. The chi-square is almost 0, and the p-value is 0.8, so this model is not rejected. In other words, the assumption of equal means is not rejected. And so we can assume that this model, or this means the model fits the data. We don't necessarily know it's the true model, but it shows us that at least this idea of equal means, this assumption here is not rejected. Let's take a look at the parameter estimates. You can see that in the unstandardized solution, the loadings are both fixed, so they're kind of boring and not relevant because those are fixed parameters. The common mean is estimated. That applies to both variables according to the model. The intercepts are both fixed to 0, so there are no mean differences here under the model. And we have the true score variance estimate. That's what goes into the numerator for the reliability coefficient. And we have the two error variances under residual variances. So those are the variances of epsilon 1 and epsilon 2. And those go into the denominator together with the true score variance to get the model implied observed variance. And so you could now use these parameters here, the true score variance and the two error variances, to calculate reliability by hand. Now, fortunately, you don't have to do that because Mplus gives you the reliability not directly under something that's called reliability, but Mplus provides the R² measure for the observed variables as part of the standardized solution STDYX. So STDYX here is the completely standardized solution in Mplus, which provides the standardized factor loadings, and at the very end also provides R². R² in this case here are the squared standardized factor loadings. And so those are equal to reliability. That's the same thing as the reliability coefficient that I showed you earlier. So this tells us that 67.6% of the variance in the measure Y3 is true score variance, and 69.2% of the variance in the measure Y4 is true score variance. So these measures are not extremely reliable. They have reliabilities that are below what we commonly consider good reliability in the social sciences. So roughly we think that something that's 0.8 or higher indicates good reliability. So this is more mediocre. There's a lot of measurement error variance here that is reflected in those measures. Now, oftentimes we're more interested in the aggregate reliability or the composite reliability. If those tests are tau equivalent, then we could aggregate them to a sum score or a composite score, and then that composite score would have higher reliability. I will discuss how to do that in Mplus, how to compute the composite reliability or reliability of the sum of Y3 and Y4 in a separate video. If you're interested, you can check that out. But so for now, so say we can see here that these individual test score variables don't have very good reliability. So if we use them individually, we'd have to be careful with those conclusions. If we use them in the aggregate, then we would get something that would be a little higher and potentially sufficient for what we want to do. So I hope that this video gave you a sense for what the model of tau equivalence is, what it's good for, how we can test it in Mplus, what kinds of parameters we get from this model. If you're interested in more psychometrics and more videos on measurement models, then check out the description for workshops that I give and other videos. Subscribe to this channel and leave a comment in the comment section, and I'll see you next time.